Okay, very good evening everyone. Okay, so today I want to teach you about group 14, which is this group 14. We covered about physical properties, which is electrical conductivity, melting point, and I add some more about first ionization energy and atomic radius. And second part about group 14 is tetrachlorides. Okay, and then about relative stability of positive 2 and positive 4 oxidation state. Okay, then silicates and silicons. Okay, first I want to start with physical properties, which is electrical conductivity. And you know that for group 14, for going down the group, we have carbon, silicon, germanium, tin, and lead. Okay, what is the difference of group 14 among the other group? Is you can see that going down the group 14, you can see that all the elements have different nature. Okay, which is carbon is a non-metal, silicon and germanium is are metalloids, and tin and lead are metals. Okay, so we can see that the electrical conductivity is become increasing when going down the group. Okay, now I want to explain you using the next page. Okay, here are the physical properties of group 14. Okay, which are atomic radius, melting point, first ionization energy, and electrical conductivity. And you can see that proton number of group 14 increasing when going down the group 14. Okay, so now when we talk about the atomic radius, you must know that what is the keyword of atomic radius. Okay, first one is the nuclear charge and followed by screening effects. Okay, and then we can see that the pattern when going down the group, so we can see that the first one is a nuclear charge and screening effects are increasing, and then okay, screening effects increasing are greater than nuclear charge. Hence, how about the attraction force? Okay, hence the attraction force between outer electrons and nucleus become weaker. Okay, become weaker. Okay, hence how about the size? Okay, so the size become increasing. Okay, how about the Z effective? Okay, as you know how to calculate the Z effective, okay, we can see that the carbon we have 6, so proton number minus the inner electron, so we got 2, so we got 4. Okay, why the silicon here have 14 proton, then 14, okay, minus 10 refer to the inner electron, then we got 4. So we can say that the Z effective is almost constant. Alright. Okay, so we can see that the pattern is the size become increasing. So what we can plot here is carbon, and then we put silicon here, germanium here, tin here, and then finally is a lead. Then you just sambung all the titik lah. Okay, and the first thing that the most important here is the axis lah. So atomic radius against the proton number. Okay, now we are done with the atomic radius. Okay, then the second one is about ionization energy. Okay, so the keyword is also same. So we have nuclear charge, we have screening effects, and then we have the atomic size. Okay, because the atomic size will affect the first ionization energy. So now is we can see that same nuclear charge and screening effects increasing. Okay, and then screening effects increasing is greater than nuclear charge. Okay, why? This is why. Okay, as I selalu explain kan. Okay, because simple quantum number of electron which occupied by electron is increasing. Okay, then what happened to the attraction force? Attraction force between particle, increasing, and then become weaker. So attraction force become weaker, weaker, and then size become increasing. How about the ionization energy? Then define what is IE. Minimum energy required to remove the first electron, and then what we can say that electron are removed more easily. Hence IE become lower. So how to sketch the IE? We have first IE here. First IE, and then the unit kilojoule per mole. Kilojoule per mole against proton number. Now you can plot the IE, which is become decreasing across going down the group. So germanium, tin here. Tin, and then we have lead here. Then just continue the. Alright. That one is the first IE. For first IE of group 14, we can see that what I plot the lead is slightly higher than tin. So they have some explanation here. Why lead of IE is IE of lead is slightly higher than tin. So now I try take a look of the electronic configuration of tin. Tin, lead is 82. Now I use krypton. Which is 36 here. And then continue by 4D10. For S2 we have 4P2 of tin. And then for lead, for lead we have 4D10, 4S2, 4P6. Now we have 4F14. Then 5D10, 6S2, and 6P2. The total is 82. So we can see that the presence of 4P14 here is cause the ineffective. Ineffective screening by 4F electrons in the lead atom why so we can see that the screening we can see here the shielding is strongest for S electrons. So the ratio we can see that like S is greater than P, is greater than D, and greater than F. Hence when the screening is less, so that the IE of outer electron of leads become slightly increasing. Higher energy is needed to remove compared to tin, although lead is a greater size. Alright, so that one is you must understand this one. Class. So now we want to see about melting and boiling point going down the group 14. As we know that carbon is a non-metal, but it is a that diamond. We refer to the diamond. Then silicon and germanium is a metallite. So these three have a giant covalent structure. Why? For tin and lead is a metal. Hence the structure is a giant metallic structure. Now here we go to the sketching graph. Melting point. As we usual do before, melting point. For the first thing is we must take a look about the bonding. Okay, hence the second point is a structure. Okay, so according to the bonding, okay, as you know that the first tree is a giant covalent structure. Okay, so you know that how the structure is. Okay, how the structure is, class, right? So the structure is a like tetrahedrally shape lah. Okay, so we have here, then we have here. Okay, then so this refer to the carbon, silicon and germanium atom. Okay, so then now we have
jatuh macam mana?
Then just draw. The minimum is 3 layers. So now this refer to the carbon atom, silicon atom or germanium atom. So you know that for the melting point, a large amount is needed to break the strong covalent bond in a giant covalent structure. Okay, hence we can see that as the size of atom increasing, like carbon smaller than silicon, smaller than germanium, so the strength of covalent bond decreases. So now we can sketch the melting point. So now it's a melting point. Melting point degree Celsius against proton number. Then we can plot C. That one is referred to diamond. Melting point of diamond. Followed by silicon. Germanium here. Tin. And lead. Then you just sambung all the point lah. So now I want to refer why tin and lead. Lead is a slightly higher melting point compared to tin. So now is because of the structure. Because of the structure of tin and lead. You can see that tin is a tetragonal structure. While lead is a FCC, face centered cubic structure, which is that one is the lead, which is more close packed compared to tin tetragonal structure. You can see that it's less packed lah. So now what happened is you can see that lead is more close packed than tin, which is tetragonal structure. So that's why the lead melting point of lead is higher than tin. For the last physical properties of group 14 is electrical conductivity. So electrical conductivity usually kita guna Ohm lah. So against the proton number. So across the going down the group 14, you know that carbon non-metal, metallite, and this one is metal lah, tin and lead is a metal. So you know that for giant covalent structure of the first three, for the first three, this one is no mobile electron, which is no delocalized electron lah. Okay. Okay, for giant metallic structure, okay, which are tin and lead, they have delocalized electron. Okay, hence we can plot lah. So carbon, okay, and then continue. Okay, silicon here, germanium here because semi metal, so it still can poor conductor lah. Okay, and then we have tin here because metal, so they have delocalized electron, and then followed by tin. Okay, so that's all for physical properties of group 14.